Hello, and welcome to our talk on Owicki-Gries Reasoning for C11 RAR. The RAR here stands for Release, Acquire, and Relaxed Atomics, which I'll describe shortly. My name is Brijesh Dongol. I'm from the University of Surrey, and this is joint work with Sadegh Dalvandi from the University of Surrey, Simon Doherty from the University of Sheffield, and Heike Wehrheim from the University of Paderborn. The core contributions of our paper are as follows. We develop a view-based operational semantics for the C11 weak memory model. This weak memory model includes both release-acquire and relaxed atomics. We also develop an assertion language for reasoning about weak memory behaviors. In our development, we can reuse the standard Owicki-Gries framework in the setting of weak memory verification. We apply our verification technique and show correctness of several litmus tests and Peterson's algorithm adapted for C11. Our final contribution is the mechanization of the semantics, the verification framework, and several examples in Isabelle Hall. To motivate this work, I would like to consider release-acquire synchronization via the message passing example that you can see on screen. The idea is that we have two shared variables f and d, where we can think of f as being a flag and d as being some kind of data variable. Initially, both f and d are set to 0. We have two concurrent threads, where thread 1 writes 5 to d and then sets the flag to 1. Thread 2 reads from the flag until the flag has been set to 1, and once it recognizes that the flag is 1, it goes ahead and reads from the data variable. In a normal sequentially consistent setting, we can be guaranteed that thread 2 never reads the initial value, and this is because thread 2 can only exit the loop once it has seen that the flag has been set to 1, and the write of the data variable occurs before the flag is set to 1. However, in a weak memory setting, this reasoning is incorrect. Namely, in a weak memory setting, if all the accesses are relaxed, the only guarantee I can provide is that upon termination, the value of R2 is either 0 or 5. To get back the expected behavior, namely the behavior one would expect in a sequentially consistent architecture, we have to introduce release and acquire annotations on our statements. Namely, a write has to be annotated with a release annotation, and a read has to be annotated with an acquire. After both these annotations are included, if the program terminates, we have that the value of R2 is equal to 5. One way to think about this phenomenon is in terms of a message sequence chart. The program on the left, with only relaxed atomics, is able to generate a trace such as the one that you see on the screen. Here, thread 2 has read the value 1 from F, however, it is still capable of reading the 0 from the D. In terms of the sequence of messages, we can think of this phenomenon as being a reordering of messages sent by thread 1. Although thread 1 has issued the writes in one order, they've arrived in thread 2 in a different order. In the presence of release-acquire synchronization, this reordering will become impossible. If thread 2 reads from a releasing write of f equals 1 in an acquiring manner, it becomes illegal for thread 2 to read the stale value d equals 0. In terms of the sequence of messages, we can think of the release-acquire synchronization as forcing the order of messages in one thread to be preserved. Our model, like many new models of weak memory, formalizes such behavior in terms of a view-based semantics. The behavior that you see on the left would be allowed by a view-based state that you see on the right. For each variable in the system, we have a timeline recording the order of values for that variable. This order is also known as modification order in some memory models. In the example state, for the variable d, we have that the order of writes was 0 for the initialization and 5 for the write in thread 1. Similarly, for the variable f, we have the order 0 generated by the initialization and 1 generated by the write in thread 1. We also have a notion of views for each thread. In our example state, we have that thread 1 has a view where it has seen the 5 for d and the 1 for f. Thread 2, on the other hand, has only seen the 0 for d, but it has seen the 1 for f. The view dictates the values that each thread is allowed to return. Once the view of a thread has advanced, it may no longer read a value behind its view. For example, thread 1 can no longer read 0 for d or 0 for f, but it can read both 5 for d and 1 for f. Thread 2, on the other hand, may no longer read 0 for f, however, it may read 0 for d, 5 for d, or 1 for f. Let's now work through an example of an execution of this program where I'll show you the states that are generated. In the initial state, there's only one possible value for both d and f, and also both of the thread's views are synchronized on these initial values. If I now execute the program and execute the write to d in thread 1, I end up with the state that you see here on the screen. Namely, thread 1 introduces a new value for d, and its view is also updated because it has obviously seen that new value. If I then execute another step of thread 1, I have a new write for f, and thread 1's view is synchronized with this new write. Now suppose thread 2 does the read from f, where it reads the value 1. In this case, the state will be updated, namely thread 2's view will be shifted to the value 1 for f. The important thing to realize is that the view of d for thread 2 is not shifted, which means thread 2 is capable of reading both 0 and 5 for d. We contrast this behavior with the corrected message passing program, namely the program that includes release-acquire synchronization. We have the same initial state as before. After performing the assignment to D in thread 1, we end up with the state that you see here on the screen. Then performing the releasing write to F results in the state that you see here on the screen. The difference this time is that the write is tagged with a release annotation, which means that if an acquiring read is performed from that write, the view of the reading thread must be updated to at least the view that includes the value 5 for variable D. In thread 2, we have an acquiring read of F. If this read reads from the releasing write that we just introduced, we end up with a new state that you see on the screen. Not only has thread 2's view been updated to the new write for F, we also have that thread 2's view of D has been updated to the value 5. The semantics I've just described is captured by a set of simple operational rules. The semantics is defined in two phases. The first phase generates corresponding weak memory events, which are captured in the labels of the transition. This includes, for example, a read event, a write event, or a read modify write event. Both the read event and the write event may be optionally annotated with an acquiring or a releasing annotation. The effective weak memory events on a shared state are defined by three simple rules. We have a rule for a read, one for a write, and another for a read modify write update, which combines both the read and a write. Looking at just the read, the idea is that we have a weak memory state, sigma, and this rule describes how the view of the executing thread, T, is updated. So here, the event A that labels the transition could either be a relaxed read or an acquiring read. W is the write that this read reads from. And because the read returns the value n, we require that the value of the corresponding W is also n. We then have two cases, depending on whether the read induces a release-acquire synchronization or not. The updated thread view is therefore constructed via case analysis, and this updated thread view is introduced into the post state, as you can see here. Further details of state components, such as the observable writes and mechanisms for updating the thread view, are detailed in the paper. Further details for introducing writes and updates are also detailed in the paper. Now that we have some understanding of the C11 state and the operational semantics, I will now describe some of the components of our assertion language. The assertion language includes predicates over weak memory state, and they allow you to reason about a thread's views of different variables. For instance, we have a definite value assertion that tells you that thread T must observe the value V for the variable X in the given state. We also have a possible value assertion which tells you that thread T may observe the value V for the variable X. The more interesting assertion is the conditional value assertion. This assertion is over two variables, X and Y, and it encapsulates the basic premise behind value transfer through release-acquire synchronization. The assertion holds if we're in a state such that if thread T reads the value V for X using an acquiring read, then we will be in a state such that thread T must observe the value W for Y. I'll explain this through an example. The following assertions hold for the state on the left. Because thread 1's view has advanced to the last write of the variable D, thread 1 must observe the value 5 for D. Now if we consider thread 2 and the variable D, because thread 2's view is at the value 0, thread 2 may observe 0 for D, but it may also observe value 5 for D. We also have that in the state shown, this conditional observation assertion holds. Namely, if thread 2 reads the value 1 from F using an acquiring read, then thread 2's view is guaranteed to be updated so that it must observe the value 5 for D. So we can now return to the message passing example and consider the assertions that we need to verify correctness of the example. The initial assertion and the final assertion of the program is fixed. We would like to ensure that if this program terminates, the value of R2 is equal to 5. And we start out in a state where both thread 1 and thread 2's views of D is definitely 0, and also thread 1 and thread 2's views of F is definitely 0 as well. To guarantee validity, we have to introduce a set of intermediate assertions that you see here on the screen. For instance, we introduce the pre-assertion for D is assigned 5 that thread 2 is definitely not able to observe the value 1 for F, and also thread 1 definitely observes the value 0 for D. In thread 2, the precondition of the loop contains a conditional observation assertion. It says if thread 2 reads the value 1 for F using an acquiring read, then it will definitely see that D is equal to 5. This allows us to guarantee that within the loop, after performing the acquiring read to F, if the value read for F is 1, then thread 2's view of D is definitely 5. From that, we can guarantee that when the loop terminates, Because of the guard r equals 1 for the loop exit condition, thread 2 definitely observes 5 for D. From that assertion, we can prove that R2 must be equal to 5 after thread 2 performs a read of D, and therefore we have our desired postcondition that R2 equals 5. To apply this chain of reasoning, we require a Hoare logic, but it turns out that because we've already introduced an expressive model of the state, namely a model that includes thread views and updates to thread views, the Hoare logic that we use is exactly the same as in the traditional setting, so the proof rules for compound statements, such as sequential composition, are exactly the same as the rules that you would already be familiar with. In the setting of concurrency, we also require a set of rules for proving stability of assertions under interference from other threads. But again here, as with the Hoare logic, we can apply the standard Owicki-Gries proof technique for proving stability. The one addition we do have to make, however, is the introduction of several Hoare triples for basic program statements. Unlike Hoare logic, which has a single rule for assignment, in the setting of weak memory, we require several depending on how the statement interacts with the global variable. For instance, we have an axiom mod last, which says that if thread T's view of x is definitely equal to n, and thread T writes the value m to x, then in the post state, thread T's view of x is definitely m. We also require some rules for reading global variables. This one says that if thread T's view of x is definitely m, and thread T performs a read of x, loading the value into register r, then in the post state, the value of the register r is equal to m. The next two rules describe how conditional observation assertions are introduced and consumed. I would now like to describe how we can prove correctness of an assertion in a program, and I'll demonstrate this using the conditional observation assertion, which is highlighted in red. Recall that the Owicki-Gries framework tells you that one must prove both local and global correctness of the assertions. Here, because the conditional observation assertion is the first assertion in thread 2, we require that the initialization implies the conditional observation assertion. This is trivial to validate because the initial assertion guarantees thread 2 definitely sees the value 0 for f, and therefore it would not be able to observe the value 1 for f. Thus, the antecedent of the condition is trivially false, and the assertion itself is trivially true. For global correctness of the conditional observation assertion, we must prove interference freedom against each of the assignments in the other thread. Stability against the update to D is trivial, because the update occurs from a precondition in which thread 2 cannot observe the value 1 for f. So once again, the antecedent of the conditional observation assertion is trivially false, and therefore the assertion itself is trivially true. Next, we check the assignment that updates f to 1 using a releasing write. This update occurs under a precondition in which thread 2 cannot see the value 1 for f, and thread 1 definitely observes the value 5 for d. What that means is we can apply our conditional observation introduction rule, and this allows us to establish the conditional observation assertion that you see on the screen. The framework that we've just described has been encoded in the Isabelle Hall proof assistant, and our mechanization includes the view-based operational semantics, the assertion language for weak memory states, all proofs of soundness of the basic axioms over the assertion language, and example proofs of several litmus tests and Peterson's algorithm for C11. Since submission and acceptance of this paper at ECOOP, we have developed a deeper integration of our theory into Isabelle Hall. In particular, we've developed an embedding with the existing Owicki-Gries framework that is a standard library available within Isabelle Hall, and this library was developed by Nipkoff and Nieto all the way back in 1999. However, their encoding was, of course, for the classical sequentially consistent setting. The message passing example that we've considered is shown here on the screen. We have the two threads, thread 1 and thread 2, the two assignments in thread 1, the synchronizing loop in thread 2, and the relaxed read of the variable d in thread 2. You can also see examples of all of the assertions that we've described. For instance, the definite value assertions, the negation of a possible value assertion, and a conditional value assertion. To perform the verification, we apply the OG-Hoare tactics applied by Nipkoff and Nieto. And what this does is it generates all of the local and global correctness proof obligations for the proof outline. For this example, we can discharge these proof obligations by the application of a simp. This now concludes the talk. In summary, our paper presents an operational semantics for a non-trivial subset of C11. We develop and describe an assertion language for reasoning over thread views in a C11 state. This is integrated into an Owicki-Gries reasoning framework for C11. And we provide proofs of several litmus tests and Peterson's algorithm. Our entire framework is mechanized in Isabelle Hall. We're currently extending this work in several different ways. One of these is an extended logic for modular, namely client library implementations. And this involves the development of a refinement theory. We're also looking at relaxing the SB union RF acyclic restriction, which would allow us to tackle the load buffering problem. We look forward to any questions you might have on this material.